and he's a good friend and valuable asset to our team. He's, as many of you know, he's considered the world's foremost authority in ionization, and I relatively recently discovered that Arnie has written every ionization standard that exists in the world, at least the initial versions of them. So you're in great hands today, and this is your opportunity to learn as much as you can from Arnie, and I'll be trying to manage your questions as they come in and feeding them on to Arnie. If we miss any of those questions, we'll get back to you in writing later on. But clearly, feel free to submit your questions. There's a, as you can see, and I see some of you already doing it, you can do it in a text format. And if you want, you can also speak. Just raise your hand in the dialog box, and I'll recognize you so that you can ask your question verbally. But with that, I'm going to turn it over to Arnie. And again, thank you for joining us. Arnie, go ahead.
Good morning, everybody. Welcome to the webinar. As Ted said, I've been involved in ionization for quite a while. For 26 years, I worked with a company called Ion Systems, which you now may know as Simco Ion. And I have spent a lot of time working with the ESD Association and various other organizations to make sure that we have good worldwide standards for ionization. So Ted, if you could put up the first slide in the presentation.
Well, I got a little surprise for you, Arnie. The first slide is a reminder to many of you. I know most of you are probably getting these announcements. And I also know that some of you are planning to register, and we're beginning to fill up the group, so I wanted to give you a heads up that we have this once-a-year training opportunity, and it is a unique opportunity in that 5 of our team experts come together for this event, and we limit the class size. We try to keep it to around 20, and with 5 instructors, it's a very unusual training opportunity and unusual student-to-instructor ratio. Lots of hands-on use of oscilloscopes, all kinds of really interesting scenarios for dealing with today's escalating technology challenges, including Class 0 and the list that you see here. So,
Ted, I'm actually not seeing that on the screen.
You're not? Oh, man, okay. Thank you. How's that?
There we go.
Great.
Okay.
You missed the opening slide, too. But anyway, this is the announcement for the workshop that you probably are receiving. And again, please, if you're interested in registering, I would suggest you do it sooner than later, because we often do sell out. Not always, but often. And you can see the early registration deadline is June 30th, and that usually triggers activity. Anyway, join us if you can, and love to have you here in the North Shore of Boston on Cape Ann with a water view. Anyway, Arnie, I'm going to turn it back over to you now.
Okay.
Let me get this going.
Okay, so we're going to show you the outline for the webinar today. First we'll talk about ionizer basics, fundamentals of how you do create ionization, and then we'll talk about some of the ionization selection criteria, how you choose an ionizer for use in a specific application. Then we'll get on to the practical considerations, how you do ionizer performance testing, how you make sure that your ionizer is actually delivering the performance that you purchased it for. We'll talk about ionizer applications, including Class 0. And then finally, we'll talk very briefly about the changes that are occurring in S2020 that in the last version that affect air ionization. So let's get right on to ionizer basics here. The primary ionizer functions are obviously to neutralize charge. And remember, the charge that we're talking about is contained on either the insulators or the isolated conductors. If we have a conductor and we can connect it to ground, this is obviously the best way to remove the charge from the conductor. But if we have an isolated conductor or we have an insulator that we cannot ground, then the ionizer is there to neutralize the charge on these objects. It's also there to counteract triboelectrification. If you have an ionized environment, the charge generation levels will actually be lower. But we should remember that ionization is there as a CDM countermeasure. We're trying to remove the charge from sensitive objects. It's not there to remove the charge from people. It's not very efficient at it. The people, Ted, you're a little quick there.
Right.
You can go back.
Yeah, I will.
It's basically there not to do anything for people. The other main use of air ionization is to reduce contamination in clean rooms. And we're not going to talk about that very much in this presentation. We're going to concentrate on the issues relative to ESD in our presentation today. Next slide. Just a quick slide to illustrate the principle behind air ionization. Basically what we're trying to do is counteract the charge on surfaces. You see on the bottom there, the charge on the surface may be either positive or negative. We don't know in advance. Triboelectrification will cause both polarities to exist in our work environments. And what we're doing is we're charging the gases in the air. We call them air molecules, but they're really the gases in the air. And we're charging them either positively or negatively. If the surface is positively charged, it's going to attract negative ions from the air, and if it's negatively charged, it's going to attract the positive ions from the air, and it's only going to attract as much as it needs to neutralize the surface. And when we talk about ionizers, we're talking about ionizers that somehow use some sort of process to charge the gas molecules in the air. Next slide. Here we see the process for both nuclear and air X-ray ionization. If we're doing nuclear ionization, the source we use is a polonium-210 source. The polonium-210 is an alpha particle emitter. The alpha particle is emitted by the source, and it actually collides with the air molecules. It's kind of the cue ball hitting the rest of the balls on the table. When it does hit a neutral gas molecule, what it does is dislodge an electron. The electron is very rapidly captured by another neutral gas molecule. It can't exist for very long in air. And once this neutral molecule captures an extra electron, it is a negative ion. It has a negative charge. Now, the gas molecule that the electron was knocked out of is now a positive ion because it has one less electron and therefore has a positive charge. So we've created a pair of positive and negative ions. The soft X-ray generator does the process very similar. The X-ray passing by the neutral gas molecule does the same thing. It dislodges an electron, creating eventually a pair of negative and positive ions. The interesting thing about these types of ionizers is they always produce these pairs of ions. So the ionizer offset voltage is always zero. We always have ionizer balance because the ions are always created in pairs. Next slide, please. The most common method of ionizer ion production is actually what we call corona discharge ionization. In this case, what we use is high voltage on a sharp emitter point or thin wire to create the ions. What we're doing is essentially creating a very high electric field at the emitter point or wire, and these are what create the ions in the air. we have several different types of corona discharge ionization. The first and oldest is the AC ionization. This is high voltage 60 hertz AC applied to a grid or a bar or a blower containing a multitude of emitter points. What we do know about these types of ionizers is that we should keep sensitive parts away from them because the AC ionizer has high electric fields that may cause damage. A second type of corona ionizer is a steady-state DC ionizer, in which we have a constant DC of both polarities is fed to, again, grids, bars, blowers, or a large area array with discrete pairs of emitters now. We have a separate emitter for each polarity. It's the most common type of ionizer that's used in sensitive ESD applications because we have control. We have the ability to control the balance of the ionizer because we have control of both polarities of the voltage applied to the emitter points. The final type of ionizer out there is called a pulse DC ionizer. And these systems generate both polarities by alternating high voltage to a single or closely spaced pair of emitter points. It's basically used in room systems where the ESD CDM sensitivity is greater than 100 volts because once again we have field at the emitter points that can interact with sensitive objects in the room. Next slide, please.
Okay, one question that came in is what about ionized air guns? Are they corona or steady?
Actually, they can be both. We can have AC blow-off guns. We can have nuclear blow-off guns. We might have a steady-state DC blow-off gun. All three technologies are possible in a blow-off gun. So the next few slides are going to show these various types of corona ionization in a little more detail. You can see the high voltage transformer here connected to an array of emitter points, and you see that the voltage on those points is going to vary usually up to about 7,000 volts peak for each polarity. The thing you need to remember here is that ionization doesn't start at 0 volts. You need a potential of somewhere approximately 3,000 volts before the ionization starts to occur. So when you look at the waveform here, you realize that only the peaks of the waveform are where ions are going to be generated. What this means is the actual efficiency of an AC ionizer is fairly low. If we were to follow the waveform and do the calculation of when we were producing ions, we find that the generation of ions occurs only for about 36% of the time for each polarity. So we don't have a lot of efficiency, we don't have a lot of time for ion production, and we usually have to use a lot of airflow with an AC type ionizer to increase the flow of ions away from the ionizer, because since the polarity reverses every 60th of a second, or 120th of a second actually, the ions that are produced at the emitter point are actually drawn right back to it. So we have very low efficiency due to this recombination. However, we do have very homogeneous ion production because we're producing both polarities in the same place. What we find is over time the stability of the system will drift to negative as the emitter points erode, and we basically have a lot of emitter points that we wind up having to maintain over time. Next slide, please. Okay, this is a drawing of your steady-state DC ionizer. You may have as much as 15,000 volts applied to each polarity. We have separate negative high voltage and positive high voltage power supplies. Once again, the efficiency is very low because the emitter points have to be fairly close together. If you were to separate them by a long distance to reduce the recombination, you would wind up with hot spots where you had some mostly positive ions in one area and mostly negative ions in another area. So we generally have to put the emitter points fairly close together. Generally, we have to have a reasonable amount of airflow going by the emitter points to make sure that the recombination doesn't occur. The emitter point density can be high in order to achieve homogeneity, which means you have a maintenance issue. But because we have control over both the negative and positive high voltage supply, we can in many instances keep the field that escapes the ionizer very low, and we can use this with very sensitive devices because we can maintain the offset voltages at very low values. Next slide. And finally, we have pulse DC. And as you see in the diagram in the lower right, what we're doing is turning on the power supplies alternately. The points are usually kept fairly closely spaced together, but because both polarities are not on at the same time, we lower the recombination rate. So of all the three methods, this is the most efficient way of producing air ionization. Homogeneity is good because we have positive and negative in essentially the same physical place. But what we've done here is by alternating the polarities, what we allow is the polarities to escape from the ionizer before the opposite polarity is turned on. What we count on is that the ions produced will mix by the time they reach the work area. And what the pulse DC system allows us to do is to create the ions at a much greater distance from the sensitive work area. If I were to compare the three methods, the AC and the steady state DC methods typically will ionize at a distance of about 1 meter. When they get much further than 1 meter, they become very inefficient. The pulse DC system can actually create reasonable quantities of ions as far as 4 meters from the ionizer. So if we put the ionizer on the ceiling of a very high room, we're still able to get very usable quantities of air ionization down to the work area. So you'll find pulse DC systems mostly used in room systems, although you will find some of them in ionizers that are used in laminar flow hoods. Next slide, please. So how do we select an ionizer? Fortunately, there is some data available that helps you with this process. You see the ESD Association technical report, TR 3.0, mentioned there, and it's called Selection and Acceptance of Air Ionizers. And it deals with the topics we have below there. Obviously, in selecting an air ionizer, you need to know what its charge neutralization conditions are, and we'll talk about how you measure those later in the webinar. But it also talks about a very interesting thing that you'll actually find in no other standard that's available from the ESD Association, and that is it talks about measuring the impact on the static problem. In other words, what effect does the ionizer actually have on the static problem you're trying to solve? So if you're trying to lower the incidence of ESD on your product, it tells you to make some measurements that will indicate that that's actually happening. If your problem happened to be contamination, you'd be told to look and see if you're actually reducing the contamination either in the air or on surfaces as a result of using the air ionizer. The bottom line here is that if the ionizer is not doing something for you that you can actually measure, there's really no reason to be using it. There are other methods of counteracting static charge generation, and they should be tried first. But if you actually have a static problem and you suspect that ionizers will solve that problem, what the standard directs you to do is to make some measurements to see whether that's actually happening. And there are some suggestions in the document of methods to do that. It talks about environmental considerations. There are things that you need to consider when you choose ionizers. One of the most important ones is obviously whether you're operating in a clean room environment or not, and the temperature, humidity, these all can affect your selection of ionizers. There are installation considerations, how you install the ionizer, how you attach it to a ceiling, how you attach it in a laminar flow hood, where you place it on your workbench. These are very, very important considerations in using the ionizer. And finally, there are operation considerations. How does it interact with your process? Are there any other things you need to consider? And finally, We not covered in this document are the class 0 in the class 0 applications, the charge neutralization parameters, the offset voltage primarily, and then finally the decay time, how fast the ionizer will work. These are also very important in class 0 applications. Next slide, please. Here's a little table to talk about the differences between corona ionization and alpha ionization. As we get to more and more sensitive devices that we need to protect, all of a sudden the idea that we might have an ionizer balanced intrinsically to 0 volts can become very important. When we are dealing with devices like the MR heads of the disk drive industry, which have sensitivities in the 1 to 3 volt range. We can achieve those low voltages with feedback systems in our ionizers and by doing very careful maintenance with the corona ionizer. But the alpha ionizer comes along with intrinsic 0 balance and may make our manufacturing a little bit easier to maintain. Because it requires much less maintenance. You'll have this slide, so I don't want to go over everything in it, but things like corona ionizer requires a power source, and alpha ionizer does not require a power source. The corona ionizer has a varying maintenance interval depending upon the cleanliness of the area, the cleanliness of the air where it's used. If you're beyond the maintenance interval, many of the ionizers now contain monitoring and alarm systems for failures. But when you look at the alpha ionizer, your maintenance interval is 12 months, and this is, a result of the requirements for owning the alpha ionizer, not because there's any failure. And in fact, there really can be no failures of the alpha ionizer. It's always going to work for you. There are some other issues. I would suggest if you're very interested in this topic, I will be teaching the ionization tutorial at the ESD Association Symposium. It's a much more detailed, it's a 3-hour tutorial, and we'll get into many more of these issues in much more detail. You can find that out on the ESD Association website, www.esda.org. Next slide, Ted.
Arnie will also be doing some unusual tests here in July at the workshop, where you'll see some of the more advanced measurements that are typically not made available, such as measuring the swing on AC ionizers, that sort of thing.
So let's talk about some of the practical considerations for using ionizers. Next slide. What do you need to know when you're going to really use the ionizer? First of all, ionizers can create decay time similar to dissipated materials, and they're a possible solution for what standards refer to as process essential insulators in the workplace. What are these process essential insulators? They're the insulators you may use to do work on your product, but really the most important process essential insulator is usually the product itself. It's not something that you can do without. It's the oxide-coated wafers in a semiconductor front end. It's the epoxy packages on your packaged devices. It's the wires that connect to your MR head. It's the glass in your flat panel displays. Almost every product that you have out there will have insulators in it, and the charge on these insulators can be a possible hazard to your product. Circuit boards are another process essential insulator that we have to deal with in electronics work areas. The ionizer requires regular maintenance and calibration. Hardly anything you use in your process is maintenance-free, and ionizers are just not going to be the first one along. When you use an ionizer, you have to establish a regular maintenance and calibration program for it, whether it's an electronic corona ionizer or whether it's an alpha ionizer. There needs to be a maintenance schedule for it. Every deployment, as I said before, should have a specific purpose and benefit and a verified benefit. If you can't find a reason to use the ionizers, don't use them. You don't need to have them in your program unless they're actually doing something for you. And once again, they are primarily for CDM control. You're not controlling charge on people. You need to, you're trying to get the charge off of insulators, and you're trying to get the charge off the insulators in your devices. To apply ionization correctly, you need to know your device CDM sensitivity. How sensitive is your device? Because that's going to determine the ionizer that you choose for your application. And I know that most of you are going to say we have a great deal of difficulty finding the CDM device sensitivity. Fortunately, in most applications in the electronics industry, outside of the MR head industry, the ionizers that are easily available have balanced voltages that are much lower than the device sensitivity, so we generally don't have a problem. But if you really are concerned that you have a very sensitive device, it's really important to find out what the actual sensitivity of that device is.
Okay,
Next slide.
I want to just take a quick opportunity here. There's a poll opportunity. What I'd like you to do is, how many of you actually go out and your company, and how many of you actually try in earnest to get HBM and CDM data, both HBM and CDM data? You could just in the poll, enter that. That would be. There's a section on your dialog box where you can actually put the tally in there. But anyway, it's critically important. I can tell you from personal experience, if you don't have and you don't go after the data, you can be burned badly with class 0 devices entering the process unknown and resulting in extremely high yield losses and reliability problems. Often, not often, but we've seen 2% failure rates. So go after the data. If you haven't done it before, make sure somebody in your company is. Thank you.
Well, that was very interesting.
Yeah.
Anyway, how about the application limitations for ionizers? What do we need to pay attention to? Most of the misapplications of ionizers tend to be through engineering oversight. And what we have here is a list of some of those things that you need to be paying attention to when you use the ionizer. First of all, a lot of metal in the area around the sensitive devices is going to absorb the ions, and it will compromise the performance of the ionizer. Field suppression, when your charged object is on a surface, the field from the object is suppressed, and it will take much longer for the ions to actually get to that surface and neutralize the charge. It's very important that the surfaces be exposed to the ionized airflow. The ionizer can't get under an object that's placed on a surface and neutralize the charge on that surface. It will neutralize the charge on the exposed surface, but the surface that is not exposed to the airflow is still going to remain charged. Teflon and other insulators that are placed on metal, because of this field suppression effect, will not ionize effectively. It will take a very long time to ionize. The metal acts as an ion sponge. It will just, soak up the ions, and they won't get to the charged object. And most importantly, when you choose an ionizer for a specific application, you need to look at the speed of motion of the objects that you're trying to neutralize, because if they're moving faster than the ionizer decay rate, the ionizer isn't going to have a big impact on their charge. So in any operation where you have moving charged objects, you need to make sure that the ionizer you choose has a decay rate fast enough to correspond to the motion of those objects. And very often, one of the most important things is to make sure that the offset voltage of the ionizer is not too high for the application. You wouldn't want an ionizer that works perfectly well in a general electronics application with an offset voltage of 20 volts. You wouldn't want to use that on an object like an MR head, which has a sensitivity of 1 volt. You need to choose an ionizer that has an offset voltage that's correct for your specific application. Here's a little graphic to talk about the fact that ions must reach the charged surface. You have an insulator here. It's charged on both sides, and you've placed it down on your work surface. And because it's an insulator, even if the work surface is grounded, it's not going to remove the charge from the insulator. It's going to stay there. Now, if we have an ionizer mounted above it, Ted, if you click again, I think the ionizer will appear. There we go. There's our ionizer. It's located above the insulator. The ionized airflow comes down and very effectively neutralizes the charge on the top surface of the insulator. But because it can't get to the underside of the insulator, the charge there is still present. We haven't neutralized the charge on that bottom surface of the insulator. Now, if we were to move the insulator up off that surface where the ionized airflow could now reach the bottom, with one more click, we'd find that the neutralization does occur. So it's really, again, important to make sure that the ionized airflow reaches the charged object. And many times when you're doing hand operations, you'll have to expose both sides of an object to the ionized airflow to effectively get rid of the charge on the object. Next slide. So how fast do the ionizers work? Well, first let's take a look at just normal air with 60% RH, and if we wanted to measure the discharge time, and we'll talk about how you can do that in a moment, we would find that it would take many, many hours, more than 10 hours, for the charge to decay from 1,000 volts to 100 volts. So without ionizers present, it takes a very long time for just the normal air humidity to take away the charge. And in many operations, we find that the humidity is significantly lower than 60% RH, which means that the discharge times are going to be even longer. Now, what we've got listed here is, several different applications of ionizers in laminar flow hoods, clean rooms, air-conditioned rooms, on workbenches, and with that compressed gas site blow-off gun that was mentioned earlier. And you can see that in all of these cases, the ionization works much more quickly than just humidity. So humidity is a very inefficient way to remove the charge from an object. Depending upon your application, these are the discharge times you can expect from your ionizer, and you can see that in some cases where you had rapidly moving objects, most of the ionizers would not be very effective. So you have to make sure that you choose an ionizer that does work fast enough to allow your object to be exposed enough to the ionized air for it to be neutralized. Excuse me.
Arnie,
Yeah, go ahead.
Really good question come in. How does humidity remove charge?
Well, what humidity does is put a layer of moisture on the surface. Excuse me. And this layer of moisture gives you a somewhat conductive path to ground. So if objects are coated with this layer of moisture, eventually the charge will bleed off, but it's really not a low resistance path. It's a very high resistance path, and it takes a very long time for that charge to go away. Humidity is much more effective at lowering the charge levels that are created triboelectrically. When you have a layer of moisture on two objects, you no longer have quite the dissimilar two objects being in contact and separation. What you have is two layers of identical moisture in contact, and the charge generation levels tend to be much lower. But as far as removing the charge, once it exists, humidity is very ineffective. When you choose an ionizer and install it in an application, you want to get it as close as you can to the charged object. So you see here the ionizer is right over the tape head in this tape machine. machine because that's where the charge is being generated, the contact of the tape and the tape head. Next slide. When you use an ionizer, you want to mark the optimum position for the ionizer because ionizers tend to move, and you want to make sure on your workbench that the ionizer is always placed in the optimum position if it can be moved. Obviously, it would be better to bolt it down if you possibly could, but in most cases we don't do that. But it is important on your workbench to mark where the ionizer should be located so that anybody working at the workbench or walking by the workbench can tell whether the ionizer is in the correct position to optimize its performance. Next slide. You'll find also, obviously, that ionizers both rotate and can tilt, so we want to mark the tilt or rotation angle on the ionizer as well to make sure that, once again, as you see here, it's facing to directly at where the sensitive product is being handled and thereby optimize its performance.
Another good question, Arnie. Can an ionizer be beneficial in a low humidity situation?
Oh, absolutely. In fact, it's one of the reasons why high humidity really isn't required in a well-designed ESD control program. The reason that we have humidity specifications and typically we find them in military applications is that when the documents that the military used were written, they were written 20 years ago, 30 years ago, and quite frankly, the ESD control materials we had at that time didn't work very well at low humidities. But that has changed dramatically over the years, and that you'll find that most of our ESD control materials, at least the high quality ones, are rated for humidities down as low as 10 to 12%. So it really isn't a requirement to have high humidity in an ESD control program, and ionizers in this ESD control program will make sure that whatever charges are generated on the insulators or isolated conductors are very rapidly removed.
Another good question, is there an easy way to tell the technology type of a given ionizer?
Well, if you're making measurements on an ionizer and you have the instrumentation to make those measurements, you will be measuring the offset voltage. If you have an AC ionizer or a DC ionizer, you will find, there may be a non-zero, even though it's a very low level. It may be non-zero, and that'll indicate, first of all, that you're not dealing with a nuclear or X-ray type ionizer, because the offset voltage of those ionizers will always be zero. Sometimes a visual inspection will tell you. Sometimes the weight of the ionizer will tell you, because AC ionizers work with a high voltage transformer. They tend to be fairly heavy. A DC ionizer will be lighter weight because it uses smaller power supplies. There's a bunch of clues if you had an ionizer in front of you that you could, take a look at it and probably figure out what type of ionizer it was. But your measurements of offset voltage, certainly if you have a pulse DC ionizer, you'll see that right away because the ionizer will be alternating between positive and negative periodically. So there are a bunch of clues that will give you an insight into what type of ionizer you have there. So from what we talked about, does anybody think the ionizer will work in this application? Probably not. It's going to not do a very good job of removing charge from that package there because the IC package is surrounded by metal. So we would not expect the ionizer to work very well here. And, quite frankly, this is not what you want to do with your devices anyway. You have metal-to-metal contact here, and if there were any charge on the package of this device, there's a very good chance that a CDM ESD event is going to occur. Next slide.
Here's a question you may have answered already, but just to be sure. how is the best ionizer position determined?
Well, well, first of all, the best ionizer position is the one in which the ionizer is directed at where the work is going on. You want the ionizer to be positioned so that the ionized air reaches your sensitive product. That's the main thing. What you will also be doing in terms of your application of ionizers is making measurements on them. And you will be able to measure what the performance would be in the area that you're working on, and you might use that same performance measurement to redirect the ionizer in some way if its position is adjustable. But basically, you want to direct the airflow to where your work is going on and make sure that it hits the sensitive product. Taking a look at this picture, can you see what's wrong here? What you have here is the ionizer on the left is actually probably directed down at the work surface, whereas the two ionizers on the right are effectively ionizing the back panel of the workstation. Certainly ions are getting down onto the work surface there, and they will be neutralizing surface charge, but they're not going to do it as efficiently as the ionizer on the left. So again, you want to direct the ionizer to where the work is going on, because that will mean that you neutralize charge the most rapidly when you do that. Next slide. Can we see what's wrong here? Do we see where the product is? And what we see here is that blue ionizer on the work surface has been turned into what we call a PCD. That is a personal cooling device. We find this a phenomenon increases during the summer months when it might be a little warmer in the work area. The ionizer tends to be turned towards the person rather than towards the work. If you had markings on this work surface of where the ionizer should be, you'd be able to tell right away that it was not in the right position. The products are there down on that carrier on the left, but this ionizer is definitely directed at the person as a cooling device. Next slide. And I think that what's wrong here is fairly obvious. The question is this an ionizer or is this a bird's nest? Ionizers must be maintained. We have to have the ionizers in a calibration system. They have to be cleaned periodically, and we have to do a procedure to check what their balance, their discharge time and offset voltage is. While this ionizer might still be in balance despite all of the debris in it, this is not the way you want your ionizers to look. They need to be cleaned periodically. Next slide, please. Okay, go ahead, Ted.
Customers freak out on me because they think ionizers are dangerous. Can there any comment on that?
I'm not sure what they mean by dangerous. Now, if you had an explosive environment, would you want to use a corona ionizer, an electronic ionizer in an explosive environment? Yeah, probably not. There are ionizers that are specifically designed to be used in explosive environments where you might have solvents or fumes of some kind. These are the only ionizers you would use in that application. Are the ionizers dangerous to people? Not that I know of. In most cases, the ionizer emitter points can be touched with the power on, and that they will be no hazard to the people. Are they a hazard to the product? Are they dangerous to the product? Yes, go ahead.
Clarification came in. The question is that they're raising the question about ozone being a problem.
Okay. One of the things that you want to know about ozone is whether your ionizer is producing ozone or not, and that should be in the manufacturer's data sheet. Most of the ionizers that are used in sensitive applications produce very low levels of ozone. If you can smell ozone from an ionizer, it's too much. That is not an ionizer you want to be using. But most of the ionizers that are used, at least the ones that are produced in the U.S., are the ozone is measured from them, and it's at very low levels, and we're talking about levels in the 5 parts per billion range, which is much lower than the OSHA requirement of less than 200 parts per billion. So ionizers produce very low levels of ozone. There are ionizers that I've seen over the years that do produce noticeable amounts of ozone. I wouldn't use those ionizers, but none of the ionizers that I know of produced in the U.S. Have significant levels of ozone. AC ionizers will produce more ozone than DC ionizers, that is true, but again, they're well below the levels that are specified for human work environments. What I would not do is to walk into the burn-in room where somebody is burning in 200 or 300 ionizers in a very small area. You'll find very significant levels of ozone in that situation, but not in any common use of an ionizer in a work environment. So how do we tell whether the ionizer is working or not? We have standards, next slide, and what we want to do first of all is to test the ionizers before and after cleaning the emitter points, because this will allow us to establish a maintenance interval. If you test the ionizer before you clean it and it's still within your performance requirements, you do nothing. There's nothing to do. At some point you'll find that the ionizer no longer meets your performance requirements. It's drifted beyond them because it hasn't been cleaned, and now you know that you need a shorter maintenance interval than the time you've waited at this point. So when you first start using the ionizers, we certainly recommend checking them monthly, but if your ionizer is still within your performance requirements, there's really nothing that you need to do at that point. It's only when you check it 1 month and you find that it's no longer meeting your performance requirements that you know that 1 month less than that is your maintenance interval. When you're doing testing, you're going to test for the static decay and balance of the ionizer. We call this the discharge time and the offset voltage. The time is going to depend on the manufacturer's specifications, what the manufacturer says the ionizer should do in terms of its operation. You're going to test for both polarities because testing one polarity will give you incomplete information. You need to test for both positive and negative, what the discharge time is, and then you'll be testing for what the overall balance of the ionizer is. You test standing behind the ionizer. You don't want to disturb the airflow during your test, and you use the industry standard test method, which is STM 3.1. It's not 2006. I'm sorry, we haven't updated this slide. It's actually 2015 now. It has been updated beyond 2006. We need to change the slide. So there are industry standard test methods you can use. These are the instruments that are used in that testing. You're going to use either a portable electrostatic field meter with a charge plate that you see on the left side, or you're going to use a self-contained charge plate monitor and timer that you see an example of on the right side. Each one of them will have a charging device that will charge the plate to plus or minus 1,000 volts. And they'll have either an integrated timer or you can use a stopwatch to do your timing. Next slide. So now you see we have the correct STM 3.1. It's the ESD Association standard. It's also the only ionization standard worldwide. It's actually incorporated in all the other international standards. You're measuring two things. You're measuring decay or discharge time, in which you charge the isolated plate to 1,000 volts, and then you measure the length of time necessary to reduce the plate voltage to 100 volts. Then you charge the plate to 1,000 volts and measure the time to reach minus 1,000 volts, and then you measure the time to reach minus 100 volts. Now, do you have to use stop voltages of plus or minus 100 volts? No. If you want a different stop voltage, you can use that. There's no requirement that you must use these voltages in your application of ionizer. Typically, the disk drive industry will do their decay time down to plus or minus 10 volts because they have very sensitive devices at the 1 volt level. So the choice of stop voltage is actually up to you. The standard, which manufacturers are going to be using when they test their ionizers, talks about 1,000 volts to 100 volts. Now, the second test you're going to do is the offset or balance voltage measurement. In this case, you're going to ground the isolated plate momentarily to remove any residual charge on it, and then you're going to place the isolated plate in the ionized area and note if there's any change in the plate voltage. For pulsed ionizers, you're going to notice that both positive and negative values will occur, that the ionizer will change between positive and negative voltages. This is normal operation for the ionizer. You record both the positive and negative peak values. For AC ionizers, for DC ionizers, you'll get a single voltage. It may be zero, it may not be zero, depending upon how well the ionizer is balanced. With nuclear or X-ray ionizers, you should always get zero balance, and if it's not measuring zero, then you need to question the accuracy of your measuring instrument, because those ionizers always have intrinsic zero balance. Next slide. Okay, we have some diagrams here to show you some of the measurements. What you see on the left is a small benchtop ionizer, and what you see on the right in the picture is that handheld field meter and isolated plate combination. You would first ground the plate momentarily to verify and adjust the meter to 0 volts. Next click. Then you would place the charge plate 12 inches downstream, or you could place it where your product is processed. When you're doing these measurements, it's very important to just do them in the same place every time, but you can choose the location and note the location in your test procedure where this measurement should be made. You're going to wait the manufacturer's specified time. For a benchtop blower, you typically are going to wait 1 minute or less. And then you're going to verify that this offset voltage meets the manufacturer's specification, or it meets your requirement. You may have a different requirement than manufacturer's specification. So whatever your requirement is, that's what you're going to verify that your ionizer is meeting that specification. Next click.
A question came in about offset voltage. If you determine that it's too high, is there a way to calibrate or fix the ionizer, or would the ionizer have to be replaced?
Okay, when the offset voltage doesn't meet your requirement, the first thing you want to do is clean the ionizers, clean the emitter points, and make sure that they have been maintained properly. The second thing to do is to determine whether your ionizer is adjustable or not. Some ionizers do have adjustments of their offset voltage, and you could, calibrate them correctly and, adjust the voltage to as low a value as possible. Other ionizers don't have that adjustment capability. Something in their design is meant to keep the voltage within the manufacturer's limits, and if it's outside the limits and it doesn't respond to cleaning, then you need to send the ionizer back for repair. Next click, Ted. Okay. So if we're going to make a discharge time measurement, the procedure is similar. You have the ionizer on the left, you have the handheld device on the right, and what you see plugged in there in the middle is a timing device. It's a device that will actually, measure the decay time. You can do this again with a stopwatch if you want. You can do this with an electronic timer of some sort. What you're going to do is once more ground the plate and verify that the zero adjustment is correct on the instrument. We're going to use some device, some other device to charge the test plate to over 1,000 volts. There are small handheld chargers for this process, or it might be contained within the charge plate monitor itself. We're going to place the charge plate approximately 12 inches downstream from the ionizer, or again, where the product is processed, you can choose the measurement location. We're going to charge the plate to 1,000 volts, and when it reaches 1,000 volts, we start the timer, and then we stop the timer when the charge plate voltage reaches 100 volts because of the ionization. We want to verify that the time to reach the targeted 100 volts meets the manufacturer's specification, or it meets your facility specification. You may have a different specification than the manufacturer. And then you need to repeat this testing for the opposite polarity. You need to test both 1,000 volts, plus 1,000 volts, and minus 1,000 volts.
Another question, Arnie. Is the standard requirement of plus or minus 35 volts a requirement or user-defined?
Well, we're actually going to talk about that, I think, towards the end when we talk about 2020 changes. The requirement in S2020 for ionizer balance of better than plus or minus 35 volts is connected to the notion that the ionizer is going to induce voltages on isolated conductors, which it will do. The voltage that the ionizer will induce on that conductor is dependent upon the conductor's distance from the ionizer. It's dependent on the conductor's relationship to ground. There are many things that affect the voltage on an object when it's in an ionized environment. The ionizers that are typically used in electronics applications today are typically balanced to better than plus or minus 20 volts, so we're really not very concerned that the ionizer is going to have create issues for isolated objects. Quite frankly, we have some arguments with this 35 volt specification because it doesn't take into consideration the capacitance or the size of the object that it's talking about. There's no mention of the size of this isolated conductor, and quite frankly, a small wire that's charged to 35 volts is going to be much less of a hazard than a large metal plate charged to 35 volts. So that whole idea of 35 volts needs a lot more discussion. Ionizers are probably not going to be the source of the problem.
Another question, would it be better to have the cord out of the way? I assume they're referring to this photograph.
This picture, absolutely. That's absolutely correct. This picture was done just to show that the cord was actually connected to the handheld device. But you would want to have your measurement area where you're measuring the ionizer, you want it to be free of obstruction. So you not only would not have the cord there, but you probably wouldn't have the timer there as well. It was just a means of getting all these elements in the picture here. So let's talk about how we look at ionizers that are going to be used in Class 0 applications. Now here's an application in the photo area of a semiconductor factory. This is where we're using ionization to protect the reticles that are used to print the patterns on the semiconductor wafers. They're actually one of the few truly electric field sensitive devices that we have, so we really don't want charge on any object in the area. And you can see in this area the ionizers have been mounted on the ceiling. It's a fairly high ceiling, but what they do is make sure that all of the objects in this particular area have been neutralized, because any electric field anywhere in this area is a potential hazard to the semiconductor reticles. Next slide. Here are your ionizing blow-off guns and nozzles. They come in many, many different shapes and sizes. What they're doing is using a compressed gas flow to remove the charge from objects fairly quickly. In some cases, not only are they meant to remove charge, but they're also meant to remove particles and clean the object. So they have a cleaning function as well. Some of them, and actually not the ones I've indicated here, there are designs of ionizers that will work in a pure nitrogen environment, and they find, applications in the semiconductor industry and other places where you have to use a nitrogen environment with the ionizer. Next slide. So what are the class 0 considerations for these ionizers? What do we need to be thinking about? Well, the first thing we need to be thinking about is whether we need the ionizer at all. If we can resolve the problem with static dissipated materials, this is a much simpler and much more consistent method, and it's not prone to human error. You can't, misdirection of the ionization flow is not a problem with static dissipated materials. So the first thing we want to look at in a class 0 situation is whether we can solve the problem with a static dissipated material. If we can't, then we're going to continue with using air ionization. We want to confirm the effectiveness with and without the ionization. We want to make sure that the charge has actually been removed from our sensitive object, so we're going to use a field meter. We may use an electrostatic voltmeter to make sure that we have removed the charge from the process essential insulator. And then we want to use EMI event detection. Have we eliminated the ESD events in the work area? We want to be sure that our ionization is actually doing something. We want to look at the type of ionizer we're using with a 200 to 250 volt CDM sensitive device. Our conventional ionizer offset voltages, which are typically less than 20 plus or minus 25 volts, are okay. But if we have, if we have a 10 volt sensitive device, a 20 volt ionizer is not appropriate. There are Corona ionizers that are available down to 1 volt. We can get Corona ionizers balanced to this level with the feedback system designs that are available today. And if we need them, then nuclear ionizers or X-ray ionizers are available, which will give you 0 volts. So we can get an ionizer to balance at very low levels. We typically recommend that we select an offset voltage between 1/2 to 1/10 of the most sensitive device. So if you had a 50 volt sensitive device, you'd probably want to choose an ionizer that had basically a plus or minus 5 volt offset voltage. Then you'd know that there was no possibility of that ionizer creating any problems on the isolated conductors of your sensitive device. And most importantly, again, we need to have process-compatible decay times. We need to have a decay time from the ionizer we choose that's fast enough for the process flow. Many electronic applications occur very slowly on a workbench when human beings are involved, but there are other processes that occur inside production equipment, and those processes may occur at a very rapid rate. We need to choose ionizers that are compatible with that process flow. Next slide.
Another question, why would someone use nitrogen gas? What's the purpose?
Well, nitrogen, first of all, tends to be much cleaner than air. When you get a compressed nitrogen cylinder, the gas in that cylinder is actually very clean. It doesn't contain moisture, it doesn't contain oil, because it hasn't mechanically been compressed. The air systems, some of them are called clean dry air because they had many filter stages to take out the moisture and the particles and the oil that might be generated by the compressing process. And the result is that you are sometimes using nitrogen because it's a cleaner gas flow source. Another reason to use nitrogen is that your process interacts with either water vapor or oxygen. There are processes that you need to eliminate the humidity from, that you may even need to eliminate the oxygen from, and you basically use nitrogen in those applications because it's the most easily available gas that doesn't contain water vapor or oxygen. So there may be reasons to use nitrogen in a process that still requires that you minimize the static charge. Now, I mentioned that the nitrogen doesn't contain any water vapor, so the humidity is essentially zero, and that means that charge generation in a nitrogen environment is going to be much higher than in any environment that does contain moisture in the form of humidity. So in a nitrogen environment, it's very important to eliminate the static charge if you happen to be handling sensitive devices in that environment. Next slide. So here are some pictures that show you ionization that's used in equipment and that needs to be CDM safe. That we need to be sure that CDM sensitive devices handled in these processes are handled safely. The ESD risks you see here are metal-to-metal contact. Charge on a device doesn't necessarily cause a problem for it, but when there is metal-to-metal contact of the device, that's when we have a problem with the ESD. When you're handling finished dies, when you're using insulated pickups and surfaces, when you have extremely sensitive devices in these applications, and you have multiple testing stations, you're going to have ESD risks because testing inevitably involves metal-to-metal contact that can't be avoided. You may have ungrounded test and transfer locations inside the equipment, and the ionizers are there to eliminate the charge when that metal-to-metal contact can't be eliminated. So the top picture you see there is trim and form. Sometimes you have leads on the device. The leads during most of the manufacturing process are connected all together with a lead frame. With all the pins of the device connected together, you don't have an ESD hazard, but at some point you do have to separate the pins. And the trim and form process is inevitably a metal-to-metal contact process. And you see the ionizer on the left of the cutting head. It's there to make sure that as parts come into the process, they are very rapidly neutralized so that when the actual metal-to-metal contact occurs, you don't get ESD events. On the lower two pictures, you see ionizers and test handlers. A test handler is a place where, once again, metal-to-metal contact is not avoidable. When you do your testing, you put the device into a socket of some kind, and the pins on that socket are ungrounded metal. You can't ground them because grounding them would make the testing impossible. So you have the possibility of charge generation, and there are a couple of ways that this can happen. So you want to make sure that wherever the testing is going on, that there's sufficient ionization to take the charge off the packages so you don't get ESD events when they're placed on the test head. Next slide.
Okay, another good question. Would it be okay to use different ion technologies in the same area at the same time, say AC and DC?
Yes, absolutely. Not a problem. In fact, when we talk about 2020 changes and the issue of room systems with S2020, we'll talk about using other ionizers in those applications to overcome the pulsing of the room system and meet the requirements of S2020. In contract manufacturing, we're talking about circuit board assembly, surface mount. We have active components that are placed onto an insulative circuit board that actually contains other insulators as well. So we have both a CDM and a CBE, CDM being charge device model and CBE being charge board event risk. So we can not only have problems of the device discharging to the circuit board, but we can have problems of the circuit board itself touching ground, having metal-to-metal contact, and causing an ESD event. Next click. We're going to use ionizers to neutralize the charge on the circuit boards before we place components on them. We're going to use ionizers to neutralize charge in any operation where metal-to-metal contact may occur. And we're going to use ionizers to neutralize charge on the component supply reels in the automated equipment. The issue here is that makers of active devices know they need to protect the parts from ESD, so they will typically package them in dissipative packaging. However, people who are supplying resistors, capacitors, which are not necessarily ESD sensitive, are not taking those precautions very often. They're using, you know, the simplest insulative reels to supply their equipment. So we have in the supply area, we can have a mix of both dissipative and non-dissipative component reels, and we sometimes want to use ionizers in those areas to make sure that we're neutralizing the charge on the supply reels. Most pick-and-place operations occur way too rapidly for ionizers to help. So when you think of the actual placing of the components on the circuit board, ionizers are not going to be useful in this application because those operations occur very, very rapidly. Fortunately, there are other ways of protecting the components, and actually it's the physics of the situation that as the component approaches the circuit board, its field suppression voltage actually decreases. So generally we don't have problems in the actual pick and place operation. Now here are some places where we do have problems. Burn-in is an area where we're placing components into burn-in boards, into burn-in sockets. We have metal-to-metal contact going on, and we have to be very careful not to damage the components in this operation of putting the parts in the burn-in boards. We use ionizers over those operations. When we're putting circuit board parts into charged circuit boards, we want to make sure that the circuit boards are not charged. We want to make sure that when they're handled in the machines that the circuit boards are not touching other metal components, because we can get ESD events happening. You see these areas where we're doing soldering, where we're doing circuit board testing. These are all areas where we have the potential for metal-to-metal contact and the possibility of ESD events. And you see that in many instances we're determining the presence of these ESD events with the ESD event detectors that you see in these pictures. Very powerful tool for determining whether your process is ESD safe. When we're ionizing workbenches, we have several ways of doing this. We have the overhead ionizing blower, which tends to ionize the entire work volume. In other words, it's going to ionize from the ionizer down to the work surface, and it's going to ionize very evenly over the entire work surface. Benchtop ionizing blowers that you see on the right are very useful for ionizing specific work points where we want to direct the ions to a specific operation. We need to be careful when we use benchtop blowers, because anything on the workbench that is between the blower and the work area is going to divert the ions. So we need to make sure there are no obstructions between the ionizer and the actual position that we need the ions to get to. The overhead ionizing blower doesn't have those problems because it ionizes everywhere. What you see here is a diagram of how we get the ionizer to have better than 1 volt accuracy and stability. What we're generally doing is putting sensors on the work surface. They work through a feedback control circuit to make sure that the ionizer balance is maintained. Without these work surface ionizers, we generally can get balance in the 3 to 5 volt range, but if we put the sensors on the near the sensitive work area, we can maintain the ionizer balance at better than 1 volt. When you're making these types of very low measurements, you need to check your test instrument to make sure it's accurate, because we've seen many situations where ionizers did not meet this very low voltage specification for offset voltage or balance, and the problem was really not the ionizer, it was the test instrument. So you need to make sure that your test instrument is well calibrated when you're going to make measurements down at this lower level. Another click and you'll see a picture of I think of a workbench ionizer also with a feedback control system. So Ted, can you give us another click there? Okay. Same thing for benchtop blowers. If you use them and pair them with a feedback sensor and a feedback control circuit, the ionizer will maintain better than 1 volt accuracy and stability, even if it's a Corona ionizer. If that's not good enough, you wind up using alpha. The nuclear ionizers are intrinsically balanced at 0 volts, and they're very useful in these very sensitive applications. Next slide. So finally, as we conclude here, let me talk about some of the S2020 changes that occurred in the last publication of the document, because they did affect ionization. Next slide. Okay, so here you see the table that existed in the 2007 document, and you see the changes that have occurred. The offset voltage acceptable is now 35 volts instead of 50 volts. This is not a major change. It was put in there to correspond to the specification in 2020 about 35 volts on isolated conductors. So I don't want to talk more about the 35 volt level, only to say that it conforms to a JEDEC recommendation at 35 volts. We're not exactly sure where that came from. And is there any data to support a need for a change to 35 volts to protect a 100 volt HBM or 200 volt CDM device? No, there really is not a whole lot of data out there to support that change. However, the change is the change, and it exists there. Now, the first box in the table says ionization other than room systems, and I basically should have crossed out the words other than room systems, because this applies to all ionization now, a 35 volt offset voltage. A room system is typically adjusted to plus or minus 100 volts. If you adjust it to plus or minus 35 volts, it will not work very effectively. So what do you do? The separate specification for room systems is no longer in the document. That second line that you see there, it has been deleted completely. So what do you do about the room systems? And I'm not sure it's on the next slide or whether I just need to talk to this slide, Ted, so why don't you give me a click there and we'll see what it says. Okay, let's go back to the other slide, Ted. So what do you do about room systems? Very often room systems are there because contamination control needs to be part of the static control program. And a plus or minus 100 volt setting on a room system is perfectly adequate for contamination control. So what do you do if you still need your room ionization system for contamination control? Well, you have really two choices. The first choice is to don't write it into your static control program. Use it, but don't make it part of your static control program. And in this case, the only caveat that I would add to it is to make the ionization system part of something else to assure that it will be periodically maintained and calibrated, because it is going to need that to work effectively. So, it needs to be somewhere in your calibration program to make sure that it gets proper maintenance and calibration. The other thing you can do is to add a tailoring statement to the static control program that deals with the room system. And typically what we say is that room ionization will be used. It's primarily there for plus or minus for contamination control, and any area where sensitive devices are handled, additional ionization will be provided to make sure that the ionization in that area meets the requirements of S2020. That's the type of tailoring statement you need. What you need to know from a technical viewpoint is a room ionizer located on the ceiling will give you a pulsed offset voltage of some plus or minus reading. If you have an ionizing blower in the same area, it will overcome that reading. it will swamp out the ionization from the room system, and you will get just the ionization from that benchtop blower. So in sensitive areas where you're using room air ionization and you need to bring the measurements in compliance with S2020, you use additional benchtop ionization to overcome the effects of the room ionizers and meet the requirements of S2020. Again, when I teach the ionization tutorial, we'll get into a lot more detail on this, and I invite you all to attend that in September. And check on the ESD Association website for the details of those tutorials. There are many other subjects that are being taught that are also very important to anyone interested in establishing an ESD control program. So I think we're at the last slide, Ted.
One more thing. Rich West has requested, he's raised his hand, so Rich, is that something you want to ask a question of the group or of Arnie?
That was just a while back when you were looking at the trim and form machine there. Since there's so much metallization there, means that the ionization fan that's left is going to be very, very inefficient. So shouldn't you be targeting that more on the input of the material? Because once you get to the track of the trim and form, there's probably not much you can do unless you can focus it.
Yeah, well, as you know, if you notice on that particular slide, that ionizing blower is located very close to the path of the product that's going into the trim and form. And at that distance, you can expect that the actual time to neutralize, even with the metal around there, is probably well under 1 second because of the proximity of the ionizer to the product path. So in that particular application, it actually did neutralize the charge fast enough to be effective in protecting the devices. And remember, we didn't have to get to 0 in this application. We just needed to get to under about 400 volts to protect the device. So Ted, you want to bring up the last slide? So our conclusion here is, first of all, air ionization is an important part of the static control program. It's there to neutralize the charge on the insulators and isolated conductors, not on the people. It is a CDM issue. We want to get the charge off the essential insulator that's part of the product itself. Applying ionization successfully does require an understanding of its capabilities and limitations. There are issues similar to the one Rich just raised, that we need to be sure that the ionization is going to work fast enough and that we need to choose ionizers whose offset voltage is compatible with the devices we're trying to protect. We need to, when we select the ionizer, we need to understand the device sensitivities and the manufacturing process both. We need to understand the static control program requirements. We need to engineer the use of the ionization for the specific application, that not all ionizers will work in all applications. We need to know that ionizers that are optimized for Class 0 applications are available, but they also need to be properly applied to be effective. You can have the most sensitive ionizer, the most well-balanced ionizer in the world, but if it's not facing the product it needs to protect, it's completely useless. We need to properly apply them. And finally, the thing I'd like to leave you with is this last statement. Static control is no longer optional. The devices we're handling today are ESD sensitive, and they're going to become more ESD sensitive with time. The requirements we make on their performance guarantees this. So static control is not optional. It is the price of admission, that if you want to be working on electronic components in modern products, you need to make sure you do have a static control program. So I thank you all for listening. If there are any other questions, Ted, I'd be happy to answer them. If you folks think of questions later on, please email them to Dangelmeyer Associates, and we'll make sure that you get answers to your questions. So thanks again.
We have one more. Is the test method to test ionized air guns the same as benchtop ionizers?
Pretty much the same. If you look in S2020, not the S2020, but STM 3.1, there is a procedure in there for testing blow-off guns and nozzles, and typically you're going to, I mean, if it's just an evaluation, you're going to hold the blow-off gun approximately 6 inches from the isolated plate. And the isolated plate is going to be located 6 inches from ground, and you're going to charge the plate and then aim the gun at the plate and measure the neutralization time. So the answer is yes, it's pretty much the same as you test for benchtop blowers. Again, you want to locate the gun where it makes sense for your process. In other words, if you're going to blow off 2 inches away from the product you're using the blow-off gun on, do your testing at 2 inches away from the charge plate. The manufacturer will do it at the distances specified in STM 3.1 because they have to generate a standard data sheet, but you can do your testing at any distance that makes sense to you.
Okay, and Robert would like to ask a question. I've just unmuted your line, Robert, if you want to ask a question.
Morning, Robert, or good afternoon, depending on where you are. I'm not hearing anything, Ted, are you?
Nope, nor am I. Since so many of you have expressed an interest in our complimentary webinars, I wanted to show you something on our website that you might benefit from that is also complimentary. Let me go there. We have this is our homepage on our website, and we have several videos here that are complimentary and short educational vignettes that on these topics that you see listed here. The other thing is the webinars that you heard today and the ones in the past have been recorded. So if you go to this link here, you can go back and review other webinars, and this one will be there in about a week or less. The other thing I mentioned earlier is the annual workshop that we do here. You can click on this link right here on the home page. In fact, I'll do it for you. And that brings you to the program and registration information. So if that's something that appeals to you, there is a good way to get to it. And let me just see if there have been any other questions. I think not. I think we're in good shape. And again, thank you all for joining us, and we'll look forward to seeing you next time.
Thanks, everybody.
And thank you, Arnie.
Okay, bye-bye.
Bye, everybody.